Okay, picture this. You wake up tomorrow and your smartphone is completely bricked. Like no Wi-Fi, no text, zero streaming, nothing. A few decades ago, that was actually just normal life. But today, computers run literally everything in the background. So, how do these magic boxes actually work? Well, welcome to the ultimate high-energy explainer cheat sheet on computer systems. We're going to speedrun the absolute essentials, so let's get into it.
Right off the bat, we're launching straight into a pop quiz. Question number 1. What exactly is the difference between hardware and software? Go ahead and lock in your answer right now. Is it literally just outside versus inside? Think about it.
All right, so if you guessed that hardware is the physical stuff, massive W for you. Hardware is the actual electronic components. You know, the things you can actually drop and break, like your monitor, your keyboard, or the CPU. Software, on the other hand, is the brainpower. It's the code, the programs, the recorded instructions that tell the machine exactly what to do. Because honestly, without software, your $1,000 hardware is just a really, really expensive paperweight.
Now pay attention, this is important for the exam. What we're looking at here is the logical structure of a computer, and it runs on something called the IPO principle. That stands for input, process, output. Basically, you feed the computer data, it crunches the numbers, and then it spits out a result. The whole system relies on 5 main players: the input unit, output unit, central processing unit, primary memory, and secondary storage. But first, let's break down the main boss here, the CPU.
So, the CPU is the undisputed brain of the whole operation, but it actually splits the workload. First up, you've got the ALU, or the Arithmetic Logic Unit. This guy is your heavy lifter. It handles all the raw math and the logic decisions. Right next door is the Control Unit. Think of this one as the manager. It doesn't actually do the math itself. Instead, it supervises, telling all the other components exactly what to do and exactly when to do it.
Okay, but how does the brain actually talk to the rest of the computer? Well, it uses the system bus. It's basically this high-speed electronic highway of connecting cables. And notice how this highway has 3 dedicated lanes. The data bus carries the actual files and info. The control bus carries the manager's instruction signals. And the address bus, that carries the exact memory coordinates, so the system knows exactly where the data is supposed to go. It's all about total synchronization.
All right, pay attention. This is important for the exam. You absolutely need to know the difference between our 2 types of primary memory, RAM and ROM. RAM is random access memory. It is crazy fast, but it's volatile. Meaning, the second your laptop dies or loses power, any unsaved data in RAM is completely ghosted. Gone. ROM, or read-only memory, is non-volatile. Its instructions are permanently burned in at the factory. They survive without power and handle the absolutely crucial boot-up sequence when you first turn the machine on. Now, RAM is definitely fast, but modern processors are way, way faster. So to stop the CPU from lagging while it waits for RAM to catch up, we have cache memory, pronounced just like cash money. This is an ultra-high-speed VIP storage lane literally built right into the CPU. When the CPU needs data, it checks the cache first. If the info is there, that's called a cache hit. And get this, like 95% of the time, the processor gets its data right from this VIP lane. Pretty wild, right? All right, time for a rapid-fire knowledge check. This is straight from the source materials checkpoint 1.1. What role does the input unit play in a computer? Take a second. How do your physical real-world movements actually translate into digital actions inside that electronic brain? Well, here's the secret. The input unit translates human actions, typing, talking, swiping, into digital binary code, zeros and ones. It's literally the only language the computer actually speaks. And you got to think beyond just the keyboard here. A mic turns your voice into binary audio. A barcode reader at the grocery store, it uses lasers to instantly measure black bars and turns them into digital data just to ring up your snacks. It's happening everywhere.
Now, because RAM wipes itself clean every time you shut down, we desperately need secondary storage for permanent memory. And just look at this massive upgrade in tech over the years. Solid-state drives, or SSDs, absolutely crushed the old mechanical hard drives because they use flash memory. That means 0 moving parts and insanely fast speeds. And check out the Blu-ray disc. It uses a hyper-precise blue-violet laser instead of a standard red one. Shorter wavelengths mean the data is packed way tighter, cramming up to 128 gigs onto a single shiny disk.
All right, trivia time. Big and clumsy computers that were prone to electric failure and basically doubled as giant space heaters. Which generation of computing are we talking about here? Was it the 80s? 90s? What do you think?
Okay, pay attention. This is important for the exam. Those massive room-sized heaters were actually the first generation, running on vacuum tubes way back in the 1940s. Just look at this timeline. In the second generation, we swapped those tubes for much smaller transistors. Then the third gen packed those transistors into integrated circuits. The fourth gen brought us the microprocessor, which is what powers your current laptop. And the fifth gen? That's the bleeding edge we're on right now, AI and parallel processing.
To truly grasp just how wild that evolution really is, let's look at the math here. An integrated circuit is basically just a tiny silicon chip stuffed with transistors. Back in 1964, engineers were flexing about packing 1 to 10 transistors on a single chip. Just 20 years later, in 1984, ultra-large-scale integration, or ULSI, let them cram over 1 million transistors onto a single chip. That insane level of miniaturization is the exact reason why you literally have a supercomputer sitting in your pocket right now.
So what is all this hardware actually doing all day? Basically, it's managing the data lifecycle. Step 1 is data capturing, pulling in real-world data via sensors or input devices. Step 2 is storage and processing. And Step 3 is data retrieval. Now, the absolute make-or-break metric here is access time. That's how long it takes to actually fetch that data. Lower access time means way less lag. And honestly, this is exactly why swapping an old hard drive for a new SSD makes a tired, clunky laptop feel brand new again.
Okay, final pop quiz. And this one actually has real-world stakes for your personal privacy. True or false? You're throwing out your old laptop. You drag all your files to the trash icon and you click Empty Bin. Is that data actually gone forever?
The answer is a massive capital F false. Just hitting delete is nowhere near enough. Anyone with basic, off-the-shelf recovery software can undelete your photos, your passwords, your docs right from that e-waste. The source material highlights a really critical warning here. Before tossing any old hard drive or phone, you absolutely have to use specific software designed to permanently shred and completely overwrite the data, so it is 100% unrecoverable.
Which, to be honest, leaves us with a pretty chilling thought. Just think about every old phone, laptop, or USB drive you've ever thrown away or traded in over the years. Did you properly shred the data? Or did you just drag your files to the trash? How much of your digital life is out there sitting in a landfill, just waiting to be undeleted? It definitely makes you look at your old tech a whole lot differently. Anyway, that's our explainer on computer systems. Keep your data safe, ace that exam, and I'll catch you in the next one.